So continue example 8 over here. So here's how I usually do it. I go, okay, well, sine of 1 over x. If, this is critical, if x is not equal to 0, then minus 1 is less than or equal to the sine of 1 over x is less than or equal to 1. See, there's no problem with sine of a number provided that number is a real number, right? I mean, and is sine ever larger than minus 1 or 1? No. I mean, sine is stuck between minus 1 and 1. So this inequality we know for sine. And then how about x squared? X squared is greater than 0 for x not equal to 0, right? So we may multiply the above inequality by x squared. Right? We have to be careful. We can't just multiply an inequality by a number if it's negative. If we do, then we have to reverse the inequality. If we multiply an inequality by a quantity which is 0, we destroy all the information in it, right? So it's important that the thing we're multiplying by is positive. That assures me that the inequality that's up there is maintained, right? So minus x squared is less than or equal to x squared. Sine of 1 over x is less than or equal to x squared. So I want to use the squeeze theorem, all right? And I'm going to use the squeeze theorem, sticking with my current lettering. I'm thinking of this as f of x. I'm thinking of this as my h of x, as in my current nomenclature. And the middle one is the thing I'm trying to calculate the limit of. This is my g of x. So observe the limit as x goes to 0 of minus x squared equals to what? It's a polynomial. We can plug the point in. 0 squared is still 0. So this is 0. And the limit as x goes to 0 of x squared is also equal to 0. So at this point, we have met the conditions of the squeeze theorem. We've got this inequality for all x near but not equal to 0, right? I mean, in fact, the inequality is true for all x, but we really just need it near 0 and not equal to 0. And I mean, if it held at 0, we wouldn't care. It's just like that's not defined in this case. So consequently, by the squeeze theorem, we find what? By a squeeze theorem, the limit as x goes to 0 of x squared sine of 1 over x is equal to 0. So that's the squeeze theorem. So we tend to use a squeeze theorem on if you have sine or cosine of like 1 over x, something like that, you should probably be thinking, yeah, this is a squeeze theorem problem. The other kind of problem that yells squeeze theorem is when you're given incomplete information. So like here's one. If x squared plus 7 is less than or equal to, well, I'll keep with my current lingo, g of x is less than or equal to uno momento. I have to come up with something. 7 plus e to the x minus 1 for x approximately 1. Well, I mean, I could say this. Let me be more precise here. For x, an element of the ball of radius, 1, let's say ball of radius 2, centered at 1, deleted. So this would be for like x, an element of minus 1 to 1 union 1 to 3. Remember we talked about the deleted ball. We could use a deleted ball to get across the idea. We need that the inequality holds for all x near the point but not equal to the point. So just for the sake of discussion, suppose that this inequality holds for, x within 2 units of 1, but not equal to 1. Suppose that was given to you. What's the limit? What is the limit? Limit as x goes to 1 of g of x. So if you see a problem like this, you don't even have a formula for g of x, right? You just have this bound for it. Pretty much you're stuck with trying to use the squeeze theorem. There's a problem like this in your homework. So what we do is we say, okay, well, the limit as x goes to 1 of x squared plus 7, what's that equal to? Yeah, 1 squared plus 7, just plug it in. Just like you said, that's 8. And the limit as x goes to 1 of 7 plus e to the x minus 1, what's that equal to? Yeah, we can plug it in again, right? So that's 7 plus e to the 1 minus 1, which is e to the 0 is, nope. Any positive number to the 0 power is 1. So that's 7 plus 1, which is 8. Aha, so the limit of the bottom function and the limit of the top function are both equal to 8 as x approaches 1. Therefore, by squeeze theorem, the limit as x approaches 1 of g of x is also equal to 8. That's the answer. Now, I have a proof of the squeeze theorem in the notes. It's about a page long, and I'm not going to go over it in class. And the reason for that is pretty simple. The techniques used in the proof of that theorem are not really the heart of what this course is about, right? We're trying to use theorems of calculus to solve problems. So if I'm going to do a proof in here, it's because it gives you further insight into the calculus we're doing. I don't think that will be the case with a proof of the squeeze theorem here. But there is a proof in my notes. It's kind of a pain. It's, wall-to-wall inequalities, of course. But the squeeze theorem is nevertheless useful. So let me take a look here at your mission 2 and see if there's anything else I should tell you. Because I'm hoping you guys will try to do mission 2 over the weekend, so you can bring me back questions if you got them on Monday, right? We have class Monday, right? See, that is a benefit that was accrued to her because she read my announcement. I know. I'm just messing with you guys. But yeah, I pushed it back to Wednesday because I wanted to have that homework posted, earlier, and I just didn't get to it. Let's just talk about mission 2, each problem briefly. I'll just kind of read through it and make a comment here, all right? So like problem 1, I say squeeze theorem. So problem 1 is almost the same as my example 8, except instead of having 0, instead of having x, I have x minus 1 squared, and I have an x minus 1 here, and I have the limit as x goes to 1. So it's similar in spirit to example 8, but it's a little bit different looking. Problem 19, I've got a limit of a secant. And so that's probably going to be somewhat similar to that secant example we did today, I think. I think problem 19 has an answer, which is infinite. Problem 20, I've got the limit of a sine plus a tangent. You'll have to look at that. Problem 21, it's like x minus 10 over x squared minus 10. So problem 21 and problem 22, they have the same formula, but they've got a different limiting point. Notice that 21 goes to 10, whereas 21 goes to minus 10. They're both from the right, but the answers will be quite different. For problem 23, I give you a rational function, and I say, find all a which give a finite limit. Actually, problem 23, I think I should work a problem like 23 for you guys right now, before we go. Here's a simpler version of problem 23. Suppose you had f of x equal to x plus 3 over x squared plus, 6x plus 5. And then the question is, calculate the limit as x goes to a of f of x for all a which give finite value. The limit of finite value. So this one here, what are you going to do? You're going to go, well, this is x plus 3 over x plus 1 times x plus 5, right? So I can calculate the limit as x goes to a of x plus 3 over x squared plus 6x plus 5. And I can plug in a plus 3 over a squared plus 6a plus 5, provided what? A is not equal to, can't have minus 1, and we can't have minus 5, right? So that's basically this problem 23. I'm asking you, work out the limit when you can, and tell me when you can't. So to figure that out, you need to figure out when the denominator in that given function can be 0. Because that's what can go bad on problem 23. Problem 24 is a polynomial times an exponential. I think there you can just plug in the limiting value. Problem 25 and problem 26, I ask you to calculate the limit as x goes to 0 for sinh, and the limit as x goes to 2, natural log of 2 for cosh. So problem 26 is the one I was talking about earlier today when I said there's a problem in your homework that's kind of like the one I did with the limit going to the natural log of 7. But it's easier. Problem 26 is easier than what I did in class. Problem 27 and problem 28 both involve the rationalization trick that we did at the start of class today. They're both involving a square root, one in the numerator, the other in the denominator. Problem 29 is an infinity minus infinity type problem. You got to make a common denominator there. Problem 30 is a squeeze theorem problem, and I say use the squeeze theorem. Problem 31 is a composition of limits problem. I'll let you think about it. It's not really that complicated. And then finally, Problem 32 is a little bit of a challenge problem. You might need to take a little bit longer to think through that one. All right. Problem 33, it's a compound fraction problem, so you got to kind of do some algebra there. And problem 34 is much the same. And then problem 35 is actually, I'm asking you to prove that the limit as h goes to 0 of cosine of a plus h is equal to cosine of a. So problem 35 is, it mirrors what I did Wednesday for sine. On Wednesday, I proved that the limit as h goes to 0 of sine of a plus h, I proved that that was equal to the sine of a, right? This we worked through. So I've asked this corresponding question, but for cosine. It's actually in the notes, so you can look there. You're not all by your lonesome, but it's very similar in spirit to what I did in class Wednesday for sine. And that's your mission 2. So it's due Wednesday. I think that should be enough time for everybody to think through it and ask me questions Monday if you got them. So otherwise, I'd say have a great weekend.